So let's see where we stopped at chapter 2. We stopped at this one. What is the confidence interval for mu1 minus mu2 if you assume the variances are not equal? So the conclusion will be different. Sometimes the conclusion is different. Sometimes if you assume the equal variances, you reject H0, for example, and if you assumed equal variances, you fail to reject H0. So it is very important assumption. So how do I make sure my data has equal variances or not equal variances? You can use the rule of thumb, this one. S of maximum, the big standard deviation divided by the small standard deviation. If this one is less than 2, you assume equal variances. If it is greater than 2, you assume non-equal variances. So, but this is a rule of thumb. You can also look at the box plot. Do we have any box plot? Let's see. You can look at the box plot. If the big one is more than 2 times the small one, you can assume unequal variances. But if the big one is not 2 times or more the small one, so you can assume equal variances. So do we have a test? We have a test actually for the equal variances. So when we practice on Minitab, I will show you how to do a equal variances test, which is very important because it may affect your conclusion. So this is the confidence interval if we assume equal variances, but now we need to calculate the confidence interval when we assume unequal variances. The difference is what? The difference is the degree of freedom will be different. So this value, t value, will be different. And I'm not going to calculate the pooled standard deviation because I'm going to work with S1 and S2. So it will be S1 squared divided by N1 plus S2 squared divided by N2. So let me write down the formula for the difference, the confidence interval of the difference between two means in case that we assumed unequal variances. It will be y bar 1 dot minus y bar 2 dot, the same thing as before, plus or minus t alpha over 2 and degree of freedom times square root, there is no SP, square root of S1 square divided by N1 plus S2 square divided by N2. And I have all these numbers, but T will be different this time because the degree of freedom is different. Degree of freedom now is 7. So, and let's use 95% at 95% confidence level. So T will be at the complement of 95 is 0.05 alpha divided by 2 and degree of freedom is 7. So I need T at 0.025 from the table and degree of freedom 7. So let's see this value. Let's find this value from the standard normal distribution, from the table, T distribution table. I uploaded this table on Canvas. So scroll down because the first two are Z distribution table. So you scroll down, add degree of freedom 7 and alpha over 2 0.025, this one. The intersection is the T value that I use in the confidence interval. 2.365, 2.365. So let's go to our slides. So this value is 2.365. Now let's plug in all the numbers we have in this formula. Y1 dot bar is 20.7 minus Y2 bar is 22.53 plus or minus the new T 2.365 times the square root. S1 square is given is 49.42. Divide by N1, which is 5. We have 5 planes assigned for the first treatment. And S2 square is 29.50.51. Divide by 6 planes assigned for the second treatment. The simple calculation, you get the lower limit is 10.93, upper limit is 7.26. So let's see if the conclusion is different or not. The lower limit is negative, upper limit is positive. So if the lower limit is negative and upper limit is positive, what is your conclusion from the confidence interval? Do you fail to reject H0 or reject H0?
We fail to reject
Very
H0.
good. So we conclude that H0, we fail to reject H0 means mu1 equals mu2. Very good. But if both of them are positive or both of them are negative, we reject H0. So the same conclusion as before. So one time we assumed equal variances, one time assumed unequal variances. We found the conclusion is the same, but sometimes it's different. And from the test of hypothesis, also we fail to reject H0. So far, the two mixtures, the improved one and the regular one, they have the same effect on the yield. There is no difference. But keep in your mind, there is something very important. Before you conclude, you need to make sure the assumptions are correct. So I will let you know what are the assumptions for the test of hypothesis in this case. And before I show you the test of hypothesis assumption, the t-test assumptions, let's look at the output of Minitab. When you ask Minitab to give you the output for the confidence interval and test of hypothesis, it will ask you, are you going to assume equal variances or not? I will show you this one later on Monday. See, I asked Minitab that assume not equal variances in this case. And he gave me information about the treatment A is mu, the mean of treatment A is mu1, the mean of treatment B is mu2, and we are interested in the difference between mu1 and mu2. Assuming unequal variances, this is the mean for the first group, second group, standard deviation, standard error of the mean, n1, n2, and give me the confidence interval. The lower limit is negative 10.93, the upper limit is 7.26. And what is the difference? This one, negative 1.82. This is mu1 minus mu, this one is y bar 1 dot minus y bar 2 dot. The point estimate of the difference. Test of hypothesis information. P-value 0.648 and degree of freedom is 7 and the T0 is negative 0.48. We got the same answer, the same numbers. Okay, so any questions so far? Again, what is the rule of thumb for the equal variances? S maximum divided by S minimum should be less than 2. If it is less than 2, you can assume sigma 1 square equals sigma 2 square. The two populations has the same variability, or the yield have the same variability for the two mixtures or the two treatments. If you have any question, please let me know. So what are the assumptions for the t-test, for the t-test? Before we take a final decision, before you take a final decision or generalize your conclusion, you need to check the assumptions of the t-test. There are two assumptions. The two samples are independent. The two samples are randomly selected from the normal distributions. The two samples are independent. What does it mean? It means like sample from male, sample from female. They are independent. Sample from group 1, sample from group 2. They are independent. A group of data from type 1, group of data of type 2, independent. A group of plants for the first mixture and group of plants for the second mixture, they are independent. So when they are dependent, they are dependent if you have only one sample, but you measured it twice. You measured the sample two times. Like I select 10 persons, 10 people, and I measure the blood pressure before and after some treatment or some medicine. So now I have two groups of data, but these group of data come from the same people, from the same sample. So I have only one sample, but the two samples of data are dependent. They come from the same persons. But in this case, they are independent. They are independent because I have five plants. The first five plants are different from the second six plants. For the first group, I have five plants. For the second group, I have six plants. I'm not good on drawing, but not bad. So the first, these five plants are completely different from these six plants. So two independent samples. The second one, the two samples are randomly selected. So if you selected some specific ones and you are biased in your selection, this is not good. These samples are randomly selected. These samples are randomly selected. And when you assign the treatments, you assign them randomly using a coin or something. And also the these samples are randomly selected from normal distribution. So the yield of those guys and the yield of those guys should follow normal distribution. But actually, t-test is robust for the normality. What do you mean? I mean, the guy who came up with these formulas assumed normality. He worked with the normal distribution functions to drive these formulas. But later they found that if normality is not satisfied, still t-test is good, give us good results. But keep in your mind the sample should be the quality of the sample should be good, or the samples are big, to make sure that if normality is not satisfied. So how do I check normality? There are many ways to check normality. One of them is you can use the normal probability plot. So this is the normal probability plot. This is the normal probability plot for the first group from many tab, normal probability plot for the second group from many tab. If you see the dots are making a straight line, so normality is satisfied. If you see the dots are making a straight line, normality is satisfied within the confidence interval, within this lower limit and upper limit. So I see these dots within the limits. These dots are within the limits. Do we have a test? We have a test actually. So you can look at the graph, the normal probability plot. I will show you how to do it by Minitab. Or you can look at tests. There are many tests for normality. One of them is Anderson-Darling test. So see, Minitab give you information about the Anderson-Darling test. Anderson-Darling test. AD and the value. This is the value for the Anderson-Darling test. I don't care about the value, I care about the B value. If the B value is greater than 0.5, normality is satisfied. What does it mean? It means H0 for the Anderson-Darling test is normality is satisfied, and H1 or HA normality is not satisfied. So you need to fail to reject H0 to make sure the assumption is satisfied. So you look at the p value. So see this p value is bigger than 5%. This value is bigger than 5%. So p value greater than alpha, you fail to reject H0. What does it mean? It means normality is satisfied for each group. So now we can make a conclusion that the mixture A, mixture B are the same in terms of yield on average. But there are many other tests. I will show you to do how to do this one by Minitab also. So this is the end of the first of part one. So let's go to part two. What is part two? If the two samples are dependent, what should we do? If you have any question at any time, please let me know. So let's see the second case. We still work with chapter 2, but we need to cover the pair DT test for the dependent samples. And also check the assumption, because the assumption for the pair T test is not about the two samples, it is about the difference. Let's see. So what if the two samples are dependent? We should use a paired t-test, paired comparison design. So let's see this design. This is very simple design. This is a special case from the complete randomized block design. The first the part one in chapter two is a special case from the complete randomized design. We have only two treatments. There is no blocking factor. Part two is pair test. This is a special case from the complete randomized block design because we have a blocking factor, but we have only two treatments. So let's see the case of the pair t-test. Let's have an example from industry, harness testing. Consider a harness testing machine that presses a rod with a pointed tip into a metal specimen with a known force. This is the testing machine. And by measuring the depth of the depression caused by the tip, the hardness of the specimen is determined. And we have two different tips are available for this machine. Those are the two tips. And we need to know which one is higher in terms of the depression or the depth of the depression. So how do I use, what is the experimental units I should use, apply these two tips? You can apply them for the specimen. So for example, if I have 20 specimens of these ones, I can assign 10 for this one, 10 for this one. This is completely a special case from the complete randomized design, which is the first case in chapter 1. But maybe these specimens are different in terms of hardness. Some of them are very hard, some of them are not hard. So maybe I know the probability is small, but maybe when I assign the specimen for this guy, I assign very hard ones, and this one is soft ones. So maybe this guy will be better than this guy in terms of hardness, not because of this one is better than this one, because of the specimens assigned for this guy is different from this one. So there is differences among the individuals, among the specimens. So how do I control this one? So design one, a number of metal specimens, for example 20, could be randomly selected. Half of these specimens could be tested by type 1 and the other half by type 2. This is complete randomized design. This is chapter 2 part 1. So the average hardness of the two types could be compared using t-test. So the 10 assigned for the first one, like the 10 plants we assigned for the first mixture. And the other 10 are like the 6 plants we assigned for the second mixture. So it's complete randomized design, but a special case from the complete randomized design. We have only two treatments. But we don't, this one doesn't work for this case because we know maize specimens are different. There is some differences among the specimens. So we should use the other design. Suppose the metal specimens were cut from different bar stock that were produced in different heats that might affect the hardness. So this lack of homogeneity between the specimens will contribute to the variability of the hardness measurements and will tend to inflate the experimental error, thus making a true difference between tips harder to detect. If we found the two tips are different, we don't know they are different because they are actually different or because of the specimens assigned to them are different. So we need to control the effect of the specimen. We need to control the differences among the specimen. So what should we do? To protect against this possibility, assume that each specimen is large enough so that two harness determines may be made on it. So each specimen will be divided into two parts. The first part will be used to test the first step. The second part will be used to test the second step. So now every specimen will be used to test the two taps. So so now I controlled the differences among these specimens. So each specimen is a block. So then randomly assign, see, even within each specimen, I will randomly assign one tab to one half of each specimen and the other tip to the remaining half. So see, for each specimen, I'm going to randomly assign which one will be tested for the first half and which one will be tested the second half, for the third one also, and so on to the last one. So now I control the differences. Like if you are going to do an experiment for people, every person will be assigned two treatments, one in the morning, one at the evening. If you are working with animals, every animal will be assigned two treatments, and so on. So let's collect data to answer this research question. Are the two tips different? We need to know the tip 1 equal tip 2 on average in terms of hardness, or they are different. So we collected data. The first specimen used to test the first step, second step, and we found the first hardness measure is 7, for the step 2 is 6. The second specimen, 3, 3. To the last one, 4, 5. So how do I work with this data? Should I work with these two groups of data are independent samples? They are not independent samples. They are coming from the same sample. I have only one sample, but I have two groups of data. So you shouldn't work with these two groups of data. You should work with the difference between these two groups of data. So we are not going to work with this one and this one are independent samples. We work with the difference between these two tips. If on average the difference is 0, it means they are the same. If on average the difference is not 0, so they are different. Okay, the statistical model will be different, will be the same, like yij equal mu I plus beta j plus epsilon ij. What we added? We added this guy. So what is beta j? Is the effect of the hardness due to this j's specimen. So this one is the effect due to treatment, and this one is the effect due to a specimen. Beta j, j from 1 to 10 because we have 10 specimens. And within each specimen, we have 2 steps are measured. The average of the first step is mu1, the average of second step is mu2. So we added one effect. The first effect was the treatment effect, but the second effect is the specimen effect. What about variability? We have the same assumption, like variability is different among poles. But the main difference is we added one more effect. So Yij is the observation on hardness for tip I on a specimen J. Mu I is the true mean hardness of the I step. We have 2 steps. Beta J is an effect on hardness due to J's specimen. Epsilon Ij is the random effect, which has mean zero standard deviation sigma I square. That is, sigma 1 square is the variance of hardness measurement for tip 1, sigma 2 is the variance of hardness measurement of tip 2. Note that if we compute the J's based paired differences, the difference will be dj will be y1j minus y2j. So this one will be d1, d2, d3 to the d10. We're gonna work with these differences. So this d1 is this one minus this one. This one is y1, 1. This is y1, 2, and so on. We can make this is I, so this is 1, this is 2, and j is 1, j is 1. So y1, 1 minus y2, 1, and so on. So we need to make sure this one is unbiased estimator. We need to make sure dj is unbiased estimator for the differences between mu1 and mu2. So take the expectation. So keep in your mind the expectation of dj is the expectation of this guy. So take the expectation of y1j minus the expectation of y2j. It gives me expectation y1j minus expectation y2j. The expectation of this guy is what? The expectation in general of yij equals the expectation of mu I plus beta j plus epsilon ij. This one equals the expectation of the first term plus the expectation of the second term plus the expectation of the third term epsilon ij. The expectation of this guy is 0. So this one is 0. So now we have the expectation of mu I plus the expectation of beta j. Actually, the expectation of mu j plus the beta j, those two guys are constant. So this is mu equal mu I plus beta j. This one is mu I. So in general, this one is mu. When you take it for 1, this one gave mu 1. This plus beta j. This one gave me mu 2 plus beta j. So this j will be cancelled with this one. So this one will be mu 1 minus mu 2. You don't need to work with this one. Just you need to be familiar with this one. That these differences, working with these differences, it is the same thing like working with these differences. I mean, this guy is unbiased estimator for the difference between the two population means. So this is a statistical model. So let's work with the test statistic. The 5 steps for the test statistic are what? Are the first step mu h0 and h1. I care about mu d. The average of the differences is 0, or the average of this difference is not 0. if the average of the difference is zero, this means mu1 minus mu2 is 0, is equivalent to the two tips are the same. The average is not 0. Whatever it is positive or negative, it means they are not the same. They are different. So this is H0 and HA in terms of the paired, when we work with the paired t-test. We do not work with mu1 minus mu2 actually. Because working with these two, it gave me information, it gave me impression like we work with two independent samples. So work with the difference. The second step, as before, you need to select alpha, like 5% or 1%. The third step, you need to standardize the sample differences. I'm going to work with the differences. So what is the average of these guys? The sum divided by n. So this average will be standardized. How do I standardize some value? You subtract mean and divide by the standard deviation. The mean of d bar is 0. Why you use it as 0 all the time? Because we work with, when we work with testers, we assume this guy is correct. We assume H0 is correct all the time. So if this one is correct, x d bar minus mu d bar, mu d is 0 all the time. This is why we do not write down 0. It is d bar, the average of the differences, divided by the standard deviation of the differences divided by square root of n. So how do I calculate d bar? Is the sum of differences divided by n. How do I calculate the standard deviation? It is the same formula. Like remember, x bar is the sum of x divided by n, but x's are d in this case. And s, the standard deviation of x's is what? 1 divided by n minus 1 times the sum of x squared minus sum of x all squared divided by n. Change x to be d, give me this formula. So it's the same formula for the mean, the same formula for the standard deviation. So do not get panic with what is d bar, sd. It's the same thing, but I'm not working with x's like in elementary class. I work with another notation, which is d. So I change x to be d, that's it, nothing else. The fourth step, calculate p-value as before. Last step, conclusion. So let's follow these 5 steps to this example. Let me write down let me do everything. Let me write down the two groups, tab 1 of data, tab 2. Tab 1 values are 7, 3, 3, 4, 8, 3, 2, 9, 5, 4. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I don't need to take the sum because I'm not going to work with the sum of the x1. The second group of data is 6, 3, 5, 3, 8, 2, 4, 9, 4, 5. Now let's work with D. Calculate the difference. 7 minus 6 is 1, 3 minus 3 is 0, 3 minus 5 is 9, negative 2, 1, 0, 1, negative 2, 0, 1, negative 1. Now I need this sum because I need to calculate D bar. This sum is negative 1. So now I can calculate D bar. D bar is the sum of D divided by N. Sum of D is negative 1 divided by 10. So D bar is negative 0.10. Negative 0.10. S of D. S of D is like the standard deviation of X, but X will be D. 1 divided by N minus 1 times sum of D square minus sum of D all square divided by N. I have sum of D, but I do not have sum of D square. So let's square every value of D. 1 times 1 is 1, 0 times 0, 0, negative 2 negative times negative 2 is 4. 1, 0, 1, 4, 0, 1, 1. The sum of these columns is 13. This is sum of d squared. Now I can calculate s of d. This one equal square root 1 divided by 9. From where you got 9? It is n minus 1, 10 minus 1. Sum of d squared is 13 minus sum of d is negative 1 squared divided by 10, 10. This number, this standard deviation of d is 1.197. Done. Now I can follow the 5 steps easily as before. I calculated d bar, I calculated s of d. So let me follow the 5 steps. The first step is h0. Mu of the difference is 0. It means the two tips are the same in terms of hardness. H1, or sometimes we call it HA, mu of difference is not 0. The two tips are different. This is the first step. Second step is alpha. Let's use 5%. Common one. Third step, let's calculate T0. Let's calculate T0. T0 is D bar divided by SD divided by square root of n. D bar is negative 0.10. Divided by SD is 1.197. Divided by square root of 10. This number is negative 0.26. This is the third step. Fourth step, calculate p-value. Our alternative is doesn't equal. When it doesn't equal, as before, the p-value is 2 times the probability of t greater than the absolute value of t0. We did that before. So this one equal 2 times the probability of t greater than the absolute value of negative 0.26, which is 0.26. You can use the table, t distribution table, to find the p-value, but sometimes works, sometimes it doesn't work. So we should use the applet. It's much better. You should use advanced calculator or Minitab or some applet on the internet, better than the t distribution table. So let's find the value from the applet. Let's click on this one and find the value from the applet in the internet. But the applet will ask me two questions. What is your T0? What is your degree of freedom? What is your T0? What is your degree of freedom? Nu or V, nu as degree of freedom. Degree of freedom is n minus 1, n 10, 10 minus 1, 9. 9. My x, which is T0, is negative 0.26. The alternative is what? Greater than or less than or doesn't equal. Choose the third one because our alternative hypothesis is doesn't equal. So this is p-value. P-value is 0.8. Very big. So I failed to reject H0. So this is p-value. Let's go back to our slides. And our p-value now is 0.8. Now we can take a decision. P-value is greater than alpha. Very big. So we fail to reject H0. So what does it mean? It means the two tips are the same in hardness. The two tips are the same in terms of hardness at 5% significance level. So they are the same. Any questions so far? Any questions so far, guys?
I have a quick question.
Yeah, sure.
Back to the slide before this. Can you remind me how again you got 13?
This number,
Okay, you said okay. I
this
didn't
is
see.
the sum of d square.
Okay, d squared. All right.
Okay.
I didn't quite. You kind
It's
of.
okay. It's okay. And any question you have, please let me know. Any other questions? Okay. So this is the output of Minitab. Again, it gave me the same results. I gave Minitab the two columns of data, and I asked him to give me the per DT test results. But actually, it gave me the DT test information and also gave me the confidence interval information. So this is N1, N2, Y1 bar, Y1 dot bar, Y2 dot bar, S1, S2, and gave me the confidence interval for the difference, and also gave me information about testing. See the same T value, T0, this one is T0, so this one is T0, and this one is P value. Our P value is very close to this one also. Ours is 0.8 from the upload. There is some differences because of approximation. So again, we fail to reject H0, which is this one. The mu difference is 0, mu difference is not 0. So we fail to reject this guy. So the conclusion is the two tips are the same in terms of hardness. What about the assumptions? They will be different for the per DT test. They will be the same, but keep in your mind, we work with the difference. We do not work with two independent groups. So the first assumption, the two samples are dependent. It means each pairs of the measurements are from one subject or one object. And the differences follow normal distribution. Not every group follows normal distribution. The differences follows normal distribution. So let's check the normality for the differences. We can look at the box plot. We see this one very close to this one very close to this one. So the data is symmetric, approximately symmetric. The histogram doesn't work for the differences because the sample is small, is only 10. So you shouldn't work with histogram when your sample is small. You should work with histogram when the sample is big. So see, it is skewed to left, but the box plot shows that it is approximately symmetric because the histogram doesn't work well when the sample is small. Should I do a test? You can do a test. You can do you can do a normality test. Let's look at the Anderson-Darling test. See, the dots are making a straight line. All of them are within the limits, and the p-value is what? Is 0.04. What does it mean? It means at 5% normality for the differences is not satisfied. So what should I do, guys, if I have this situation? What should I do if I have this situation? If normality is not satisfied, I see normality is not satisfied at 5%, because so now I cannot make a conclusion. I should stop because normality is satisfied. Although t-test is robust for normality, it means even if the normality is not satisfied for the t-test, still I can use it. But you shouldn't have big outliers. It's something like serious outliers. I do not see some serious outliers, but in terms of the normality, how do I solve this problem if normality is not satisfied? You have any idea? So normality is not satisfied in this case. How do I fix this problem?
Just a guess. Maybe repeat the experiment a couple more times. Get a large data set.
That's very good. You can increase the sample size. You can do the experiment more times. You can test the two tips for something like 10 more 10 more specimen. So you can get more data. You can get a maybe the normality will be satisfied at this time. This is one of the solution. What else? Very good. So what else?
Can you normalize the value?
Very good. You can normalize the value. You can. How do I normalize the value? You can take a transformation. Like you can take the log of the values, the y's, or you can take the square root of y's. You can take a. So you may find some transformation. So how do I find the transformations that make my data follows normal distribution? I will show you one method. It's called Cox-Bucks method. This guy came up with some idea that can be used to fix the normality of the data. We work with this one later. We learn step by step. So PER-DT test is a special case from randomized block design that will be covered in chapter 4. But part 2 is a special case from the randomized complete block design, which will be in chapter 3. Any questions so far, guys? Any questions?
So I was just like wondering, would it be possible if you have like a very large sample, could you like fix the normality issue, like if you drop all the extreme outliers and stuff like that?
Okay, dropping the outliers is very serious point. What do you mean? I mean, if the sample is very big enough, you can drop the outliers, but you report that you dropped those outliers and you have some reason, you can write down the reason. So maybe if you drop the outliers, normality will be satisfied. It happens. Very good. This is one of the solutions also. Maybe normality is not satisfied because of some outliers. So you should be very careful with the outliers also. Thank you so much. Any other questions? Okay, have a great day.
Thank you.
You're welcome.
Thank you.
Thank you.
Thanks.
Have a
Thank
good
you.
Thank you.